so we're going to focus now on doing a little bit more algebraic limits. So there's some limit properties that we can use. So constants don't affect the limits process. Okay, so that c on the outside, we can just take the limit of f and then apply the c afterwards. If we have a sum of limits, a sum of functions, we can just take the limit of those two parts independently of each other and then add those limits together. If you have a product, we can do the same thing. We can take the limit of this part separately here, and then we can take a limit of the g part separately here, and then once we figure out the limits of those two separate parts, we can multiply them together, and that's the limit of that whole function. So if it works for multiplication, it must be the same for division, so we can take the limit of the numerator and the denominator separately if we want to know the limit of that expression. So if we have something that looks like this, we can take the limit of each part separately. So I can do the limit of this part, so limit as x goes to 3 of the fifth root, and we can do that separately from this part here. In fact, we can break this up into two separate limits. We can do the limit as x goes to 3 of e to the x, and we can divide the limit as x goes to 3 of 1 plus log x. Okay, and then we can do the limit plus the limit as x goes to 3 of sine x, and we can multiply that limit with the limit as x goes to 3 of cos x. Okay, so all those parts can be done separately. We can I could just plug in now and just evaluate all those limits. So essentially, we don't really need to write this all out again. We could just evaluate the limit as is. So same thing with powers. If we have the limit of some base in a power, we can find the limit of the base first and then apply the power after the fact. Okay, so let's take a look at some of these where we can apply these. So I've defined two limits here, the limit of f of x as it goes to a equals L, and the limit of g of x as it goes to a equals m. So if I have this power here, what I can do is I can apply the limit to the base as x goes to a of f of x. I can apply that limit first and then apply the power k. So the limit as f of x goes to a, we know that is equal to L, so it's going to be L to the power, power k in this case. So it'll be L to the power k. Okay, so we can just apply the limit to the base and then apply the power afterwards. Here we can then apply the limit separately. So I could do limit as x goes to a of f of x, and I can separate that out from the limit as x goes to a of g of x. Okay, so this becomes L times m. Here we can separate all these parts out, so we can do the limit 2 times the limit as x goes to a of f of x divided by the limit as x goes to a of g of x, and then we can apply the power after the fact. Okay, so let me just move this over. Okay, so then this becomes 2 times L over m and we can apply the power 3 afterwards. So it becomes 8L over M. So L cubed, M cubed. So here we have the limit as x goes to a of this expression. Well, I can do the limit as x goes to a, it's just going to be a. The limit as x goes to f, it's going to be L. And all that can be applied to the limit of the power, which is m. So I've kind of skipped a step right in the limits, but as I get better at this, I can start compressing some of these. So these are some limit properties, and so basically the limits can be applied to parts of expressions, and then the expression be evaluated after we apply the limit. So let's take a look at this one. This is, we start talking about endpoint behavior. So we want to know what's happening when x is going to go to infinity. So what's happening at the end? So endpoint behavior can be expressed with these relative powers of functions. This only works for x goes to infinity. And it tells us what's happening as x gets really large. Okay? Now, if we're doing local behavior, this relative power will not work. But for endpoint behavior, powers of when x goes to infinity or negative infinity, we can apply this relative strength of functions. So basically the middle function is going to be our linear function. Okay? Everything's kind of relative to that middle function. And anything as we increase the power, so this is all the polynomials here, all the polynomial powers as n gets bigger than 1, we're going to be stronger than x to the power 1. The next most powerful function is going to be our exponent. So as x gets large, it doesn't matter what's happening with the base here. Since that power is fixed here, this power will eventually outgrow this power over here. So the exponential function at infinity will always outgrow the polynomial power. And then I put x factorial here as well because that's the most powerful one we've run across so far. If we have never seen this before, this is just whatever number times itself all the way down to 1. So this is the most powerful one that is even more powerful than our exponential because here we have the number of terms is going to match that, but then the base or the multiplier is increasing all the time here. So if we go the other way, if the polynomial power n is more powerful, the root n is just as weak, okay, because it's an inverse operation. So it's just going to be just as weak, and as exponential power is more powerful than the polynomial, the log, which is an inverse, should be weaker than the root function. So when I look at this problem up here, then I can just say, well, the numerator is much stronger than the denominator because the numerator is an exponential and the denominator is a polynomial. So we end up with a situation where we just say this, well, this ends up as a weak over strong argument. And weak always strong always goes to 0. And that's good enough. And that's very important for us to be able to do because algebraically, how would we simplify this? How would we get rid of that infinity in the denominator? We can't. So, oops, I got this backwards, don't I? This is a strong over weak. So e to the x is our strong function. And x squared is our weak function, so then it must be the reverse. So strong over weak is 0. Weak over strong is 0. Strong over weak always ends up going to infinity. Okay, because the denominator grows much faster than our numerator, I should say this correctly. Our numerator grows much faster than our denominator. Okay, so strong over weak means that the numerator is going to outgrow the denominator, which means they're going to get an infinite limit. Okay, so this is what we call endpoint behavior. And we can use this relative strength of functions to help us analyze endpoint behavior, especially when we cannot simplify it algebraically.